Dear students, this is the video in which I want to do the last part of the application for Gauss's law, and that is application number 3, which is field due to a uniformly charged thin spherical shell, and probably this is the last discussion of the chapter itself. But uh, what I thought is uh, I've missed one important discussion which could have done before the starting of this application of Gauss's law, but I forgot to do that. So tomorrow I will be completing the very small short portion of this chapter itself. That means today your chapter is not going to conclude. So this chapter will be concluded by tomorrow. And in fact, this is the last discussion of the chapter by order. So in this chapter, we are discussing field due to a uniformly charged thin spherical shell. So first, we will discuss field outside the shell. Field outside the shell. Field outside the shell. So spherically charged, thin spherically charged shell. So I want to make a spherically charged shell. So this is my spherically charged thin shell where the charges are on its surface, and let capital R be the radius of this particular thin spherical shell, and let sigma be its surface charge density. Sigma be its surface charge density. So sigma is the surface charge density of this spherical shell, which means surface charge density is nothing but it is a charge per unit area. Therefore, sigma is nothing but sigma is total charge on its surface. If it is q, then q divided by 4 pi r square is the surface area of this spherical shell. So sigma is your charge per unit area, or charge divided by the surface area of the sphere is your surface charge density. So it is given to us. Now what we want here is we want to calculate the value of an electric field at a point outside this shell. Suppose this is my shell. So at any point outside this shell, suppose this is the point, I want to calculate what is the value of the electric field due to this spherical shell. So what I want to do here is I will assume a Gaussian surface passing through the very point at which you want to calculate the value of electric field. So this is my Gaussian surface which passes through the point at which you want to calculate the value of electric field. If this point is here, then this Gaussian surface will pass through that point, and it should be outside the shell. And let r small r be the radius of this Gaussian surface. So this is our Gaussian surface here. Gaussian surface. So in this case, your Gaussian surface is spherical surface itself. Gaussian surface is also in spherical shape. So as usual, I want to calculate what is the net flux flowing through this Gaussian surface. So first of all, net flux or net electric flux flowing out of the Gaussian surface will be nothing but it is E dot A. And here A is nothing but A is the area of the Gaussian surface itself, and at this point E will be outward because electric field due to the spherical charge will be outward at every point on the surface of the Gaussian surface. If at this point on the Gaussian surface the electric field even will be outward, so at every point on the Gaussian surface the electric field will be actually outward. Since area vector for the Gaussian surface will be also be outward, area vector for the Gaussian surface will also be outward at every point. Here your electric field is also outward and area vector is also outward. That means there is a 0 degree angle between E and A. So EA cos theta, where theta is your 0 in this case. So this is your flux. So flux will be equals to cos 0 will be 1. So E A. And E, and what is the A? A is nothing but A is the area of the Gaussian surface, or surface area of the Gaussian surface is E into 4 pi small r square. Because I am calculating the value of the electric flux through the Gaussian surface, so I am utilizing the area of the Gaussian surface, which has a radius of small r. So this is the equation 1. Now according to Gauss's law, what we have is total flux through any closed surface is equals to charge enclosed by the surface divided by free space permittivity. So here is your Gaussian surface. So what is the charge enclosed by this Gaussian surface? So charge enclosed by this Gaussian surface is nothing but it is the total charge of the spherical shell itself. So what is the total charge of the spherical shell? We don't know, but what we know here is we know the surface charge density of the spherical shell and the area of the spherical shell. Hence the total charge enclosed by the Gaussian surface is the total charge contained on this spherical shell, and it will be equals to charge density of the spherical shell multiplied by the area of the spherical shell itself. So that is your Q. Q will be equals to sigma into 4 pi r square. So this is the total charge enclosed by the Gaussian surface, or it is the total charge contained on the spherical shell. So Q will be replaced by pi is equals to sigma into 4 pi r square divided by epsilon 0. So this is your equation number 2. Equation number 2. Now comparing 1 and 2 again. Comparing 1 and 2. What we will get is this one is your 1 E into 4 pi r square. E into 4 pi r square will be equals to sigma into 4 pi r square divided by epsilon 0. Okay, so what things, okay, if you want to cancel out things here, so 4 pi will get cancelled, so value of the electric field will be E is equals to, if r square goes to downward, so sigma r square divided by epsilon 0 r square, because this r square divides this thing when it goes to the right hand side. So this is the value of the electric field outside the thin spherical shell. Or we can write this in another form also, most usable form or most utilized form, and that is what we do here is we just put the value of sigma to be equals to Q divided by 4 pi r square. So replace sigma by Q by 4 pi capital R square. Then what will happen? So replacing sigma by Q divided by 4 pi R square, then I'll get E is equals to Q R square divided by 4 pi R square epsilon 0 R square. R square get cancels. So the value of the electric field will be Q divided by 4 pi epsilon 0 R square. So this is the value of the electric field due to a shell at a distance or outside the shell. This is the value of the electric field due to a shell uh, at a point outside the shell, and the direction will be again equals to will be normal to the area vector itself. So at every point outside the cell, the direction will be outward normal at the surface itself. So if this is the normal direction, then the value of the electric field will be towards the direction of the normal. That means the direction of the electric field can be simply given by this normal vector. Now if you see this equation closely, this equation is actually the electric field due to a point charge. Suppose this is my point charge, and at any distance, r distance from this charge, the value of the electric field will be q divided by 4 pi epsilon r square. That means this particular formula or this particular derivation or this particular relation is the electric field due to a point charge, and for a spherical shell it resembles with the electric field due to a point charge. They are similar. This is the electric field due to a point charge at a distance of r, and this is a electric field outside the shell due to a spherical shell. So what we imply here is we can conclude that this particular spherical shell will behave as if the total charge of this spherical shell will be concentrated at the center of the cell, such that at a distance r from the center of the cell, at any point at a distance r from the center of the cell, the electric field value will be equals to this much. So this is the conclusion. This particular spherical shell will behave as if the entire charge of the shell is concentrated at its center. Hence, at any distance from the center, the value of the electric field will be this much or this much. So this is the value of the electric field at outside the shell due to a spherical shell. Now let us calculate what will be its value inside the shell. Now field inside the shell. Suppose this is my spherical shell, uniformly charged spherical shell. And suppose capital R is the radius of the shell. Now if you take a point, any point, this point, I want to calculate the value of the electric field at this point inside the cell, or we can choose any point inside the shell. So I've chosen this point inside the cell. So what your first step is, so you will make a Gaussian surface passing through that particular point at which you want to calculate the value of the electric field. So I have constructed a Gaussian surface which has a radius of small r, which passes through the point at which you want to calculate the value of the electric field. Now, in similar manner, electric flux through this point will be, let us take electric flux through the Gaussian surface, if any Gaussian surface will be E dot A, let us take, or E, suppose E to be in this direction and A to be in this direction. Again, E and A have same direction, so it is just EA. So this is flux, and this is your equation 1. Or phi is equals to, what is the area of this A? Area, Gaussian surface area is 4 pi small r square. This is 1. Now, according to Gauss's law, the total electric flux through the surface, through any closed surface, through any Gaussian surface should be equals to charge enclosed by the surface divided by the epsilon divided by the free space permittivity. But in this case, if this is a Gaussian surface, then what is the charge enclosed by the Gaussian surface? Because all the charges are outside the Gaussian surface. That means this Gaussian surface do not encloses any charge in real. Hence, the charge enclosed by the Gaussian surface is 0. Hence, the value of the flux will also be 0. So this is equation 2. So compare 1 and 2 again. So comparing 1 and 2, what we'll get is E into 4 pi r square will be equals to 0. That means since 4 pi r square cannot be 0, this is the area of the Gaussian surface, this cannot be equals to 0. That means E will be equals to 0. So this is the value of the electric field inside the thin spherical shell. So at any point inside the thin spherical shell, the value of the electric field will be 0. There will be no electric field at all, because this any Gaussian surface inside the shell will not enclose any charge. So if any Gaussian surface inside the shell will not enclose any charge, then the value of the flux will be 0. If flux is 0, then the value of the electric field will be 0. So this is it for today.